Hello students, this is a faculty from Assam Civil Engineering classes, and we are going to see the video solution of a civil engineering paper of Assam PSC that was recently held. So let's continue with our discussion. So you can see the first page of your paper, and we are going to see the solution. So moving on to our first question. The question says, identify the correct free body diagram for the beam shown in the figure below. So first, let's understand what is free body diagram. What is a free body diagram? In short, we call it FBD. So when we remove all the support conditions and just depict the support loading that's acting through that support, we call it FPD. Suppose there is a there is a fan in everyone's houses. So suppose this is a fan. My drawing is very horrible, and they forgive me for that. So there is fan that's connected to a rod and two hooks in your roofs. So if we cut it here and just depict the load that's acting through that, so this is gonna be your free body diagram. This is going to be a free body diagram because we have freed the body and just showing the loading that's acting through those supports. So let's see what are the types of supports. Let's see what are the types of supports. So moving on to types of supports. First support is simple or free or roller or rocker support. Support on which beam rests freely. So in this support, only the vertical reaction is developed. So only vertical movement is restrained. Rest delta H, that is movement in the horizontal direction, and rotation, that is rotation and movement in the horizontal direction in either direction. Either sense is permitted. So just vertical reaction is available here. Okay, so moving on to our second support, that is hinged or pinned support. In this, two movements are restricted. Delta V, that is vertical movement, and delta H, horizontal movement. So beam is not allowed to move in the horizontal direction, neither in the vertical direction, both up and down, nor left and right. So there are two reactions we taken in a positive sense. Rightward RH is positive, and vertically upward RV, positive sense. Okay, so RH and RV will be developed. So here only rotation theta is permitted, so beam can rotate here. It can form a angle theta at the supports. So moving on to the next type of support. This is fixed, built-in, or encaster support. Fixed, built-in, or encaster support. So here is a cantilever beam. You can see it in your balconies. There is a cantilever there. So there is a fixed support here, and there is a beam. So it will offer three reactions: one moment, and two reactions, RH and RV. So it restrains the movement of the beam in both in position and direction. So three reactions are developed. Neither delta H is possible, neither delta V is possible, nor theta is possible. Okay. So moving on to our next type of support, that is inclined roller. So here is a roller. It will offer the reaction inclined because the roller is inclined. The surface of the roller is inclined. So it will offer a reaction at an angle theta with the vertical. So there are two unknowns, R and theta, or reaction, horizontal reaction, RV or and RH. Because this R can be, it can have components in the horizontal as well as vertical direction. So R is equal to root of RV square plus RH square. So the next support is guided roller support. What this support does is it restrains the movement of the beam only in vertical as well as the rotation. So both M and RV are developed. both a delta V, that is movement in the vertical direction, and rotation are restrained, but the movement of the beam in the horizontal direction is permitted. So moving back to our question. This question says, what are the free body diagram? Here is a hinge support, here is a roller support, load is acting inclined. So there will be two reactions at the left one and one reaction at the right support. So there we have to find two reactions. So these both options are wrong totally. So moving on to our option B, there is a load acting in inclined way. That's inclined. It can have two components, one horizontal and one vertical. The vertical will be balanced by vertical reactions and horizontal will be balanced by horizontal reaction, and reaction is rightward because load is acting leftward. So this is the correct option B. Okay, so moving on to our next question number 2. If two forces, each of magnitude p, act at an angle theta, then the resultant will be. So we have studied the parallelogram law of vector addition, parallelogram law of vector addition. So what it says is, if there are two forces acting at an angle theta with each other, there is P1 force, there is P2 force, P1 force, P2 force, then the resultant will be given by expression P1 square plus P2 square plus twice P1 P2 cos theta. So here the question says two forces act of equal magnitude. So we can see P square plus 2P into cos theta, because the magnitude of P1 and P2 is equal to P. So let's solve it, taking this P square common. So outside the root it will be taken as P. Then taking this 2 common, root 2, then square root of 1 plus cos theta. So 1 plus cos theta you must have studied in your trigonometry classes. It's a 2 cos squared theta by 2. So we have to do square root of this one. So square root of this one, it will be like 2 root 2 into cos theta by 2. So root 2 into root 2, it will become 2. So the final answer will be 2p cos theta by 2p cos theta by 2. So 2p cos theta by 2 option will be A option. Okay, so moving to our next question. The question says, the moment of inertia of a triangle of base B and height h about the base will be. So here's a triangle, I've drawn it to avoid loss of time. So there is its apex. Let's call the axis XA. Let's call this axis G, because this axis is passing through the center of gravity of the triangle. And definition of center of gravity will be when the point through which all the mass, or in plane lamina we can call it, where all the area is concentrated. And the base, this is the base of the triangle, and we can call this axis XB. So let's see what is the moment of inertia about both all the three, apex and gravity, center of gravity, and our base. But it has asked about base, but we will see all the three. So about the apex, it will be like bh cube upon 4. So h is the height of the triangle and b is the base width, so it will be bh cube by 4. Then moment of inertia about the center of gravity will be bh cube by 36. bh cube by 36. and the moment of inertia about base, what's asked in the question is bh cubed by 12. So we have got our answer. We can easily derive it in our detailed discussion in our classes. We will be deriving it as well. So our correct option is option B, bh cubed by 12. So let's move on to our next question. The question says that force in the system shown in the figure below, and it's asking about coplanarity of the forces, whether they are coplanar or whether they are concurrent or whether they are non-coplanar. So let's see what are the coplanar forces. So suppose I've drawn this diagram. Suppose there is a beam and load is acting upon it. There will be a load acting upon it, vertical load, and there are reactions, just like the simple support as we saw in the first question. So there will be a vertical reaction, horizontal reaction, and there will be a roller support where there is just vertical reaction. So all the loads are acting in the same vertical plane. They have to act in the same vertical plane, otherwise this beam will be subjected to torsion as well. So these all the four loads are coplanar. But what are the coplanar forces? Suppose this is a plane, and there are loads acting in this plane. So these all forces are coplanar forces because these are acting in the same plane. And what are concurrent forces? So suppose this is a point, and loads are at three loads, or suppose n number of loads are acting towards this point. They have the line of action passing through same point in the space. So these are concurrent forces. So as we have seen in this figure as well, so the answer of this problem will be coplanar forces. Answer is C, because these are acting in the same plane. Otherwise, this beam will be subjected to torsion. Now moving on to our next question, unit of surface tension in SI unit. Let's first understand what is surface tension. So as you have seen, suppose there is a beaker or some utensil you have in your home as well. You keep water in it. So the water, the water molecules that are deep inside, these molecules are subjected to forces of cohesion from all four sides from the other water molecules, and these forces are equal and opposite, so these are balanced. But the water molecules that are at the nearer to the surface or at the surface, these are subjected to cohesive forces from the water molecules from below, but there is air above it. So these air molecules apply adhesive forces, but these are very small in magnitude as compared to the cohesive forces. So these water molecules at the surface are subjected to net downward force because of cohesion. So and the water molecules in contact with the surface of the utensil or beaker, these are subjected to adhesive forces as well. That is also of a significant magnitude. So these remain at the place where they were. So overall, this surface forms like a membrane, acts like a membrane, and that is stretched. So you might have seen experiments, or you might have done it in your school days, that you can place a blade horizontally, smoothly, and very smoothly over it, and it will not, submerge. So this is what we call it surface tension. As the name itself tells it, that the surface of the beam is in surface of the water is in tension. So let's see what is the formula of surface tension. So surface tension is defined as force per unit length. So what is the unit of force? That's Newton. And what is the unit of length? Let's take it in SI unit. So that's meter. So the unit of surface tension can be Newton per meter. So option D is most appropriate one. Let's move on to our next question. Is a system of forces, F1 10 kilonewton, F2 20 kilonewton, F3 we have to find the magnitude for establishing the equilibrium. So what is equilibrium? We have studied in school days as well. When the forces are acting upon a body are balanced, so that body is said to be in equilibrium. So let's establish the equilibrium here. So our F3 can have two components, F3 vertical, F3 horizontal. So let's see the component. Here the angle is 45 degree. This angle will also be 45 degree because entire angle was 90 degree. So F3 horizontal will be F3 horizontal will be F3 cos 45. It will be F3 by root 2. And F3 vertical will be F3 sine 45. It will again be F3 by root 2. So establishing the equilibrium, the horizontal force F2 must be balanced by horizontal component of F3. So F3 horizontal, making sigma fx is equal to 0. So F3 horizontal equal to F2. So F3 is equal to 20 kilonewton. So F3 is equal to 20 root 2. Again, sigma Fy is equal to 0. So F3 vertical is equal to F1 is equal to 10 kilonewton. 10 kilonewton. So F3 is equal to again 10 root 2. As you can see, the F3 coming from this and F3 coming from this are different. That is, in with this orientation of F3, we cannot establish equilibrium by any magnitude of force F3. So the correct answer will be D, will not be in equilibrium whatever the magnitude of F3 may be. So moving on to our next question. So let's see what the next question says. The question says for a given material ECK, let's see what we'll see what ECK and M are. Young's modulus. So E is Young's modulus, okay. C is shear modulus and K is bulk modulus, and they have given it as a Poisson's ratio. Then which of the following relations does not hold good? That is very important to notice. Does not hold good. So see, E is Young's modulus, C is shear modulus, K is bulk modulus, and we call Poisson's ratio as mu in the standard literatures, and in many literatures they call it as 1 by m. The mu Poisson's ratio can be called as 1 by m. So we see the relationship between these elastic constants. These are elastic constants. So relationship between these elastic constants is E is equal to 2c into 1 plus mu, where C is shear modulus or modulus of rigidity. We call it as modulus of rigidity as well. So 2c into 1 plus mu is equal to 2c into 1 plus 1 by m. Then E is equal to 3 k into 1 minus 2 mu, or is equal to 3k into 1 minus 2 by m. And the third relationship is E is equal to 9kc upon c plus 3k. Okay. And the fourth relationship is mu is equal to 1 by m is equal to 3k minus 2c upon 6k plus 2c. Okay, so let's see which option is wrong. So 9kc upon 3k plus c, that's right. Okay, then this one, 2k into 1 minus E is equal to 2k into 1 minus 2 by m, I think this is wrong. Here there should be 3k, like I have shown you. E is equal to 3k into 1 minus 2 mu. Then option C is E is equal to 2c into 1 plus 1 by m. That's right, 2c into 1 plus 1 by m. And option number D is 1 by m is equal to 3k minus 2c upon 6k plus 2c. Okay, so mu is equal to 1 by m is equal to 3k minus 2c upon 6k plus 2c. Okay, so option number B is the correct option because it has fault in it. Okay. Then comes our next problem. The failure plane at 45 degree indicates what? Okay, so let's see what the failure plane at 45 degree indicates. Okay, this problem has somewhat fault in it. It does not tell about the type of material, whether it is a ductile material or whether it is a brittle material, and the type of loading. So see, if there is a brittle material, suppose an element of brittle material has been taken, and there are normal stresses acting on it, sigma x, and suppose there is sigma y, and there is sigma y. Okay, sigma y and sigma x. So brittle materials, when acted upon by normal this has to be a ductile material. Okay, so when ductile materials are acted upon by normal stresses, so in this case the ductile materials are weak in shear. Ductile materials are weak in shear, so it will fail in shear stress. So the maximum shear stress plane lies at 45 degree from the maximum maximum principal stress plane. So this will be, suppose this stress has a larger magnitude than this one, so this will be major principal plane. So major principal plane से ये 45 degree पे होगा maximum shear stress plane, and it is this plane at which the ductile material will fail. Then comes our brittle material. When it is acted upon by pure shear, now there is no normal stress in this one. So when the brittle material is acted upon by pure shear, then there is a diagonal plane where the tensile stresses are acting. So it is this plane from where the brittle materials will fail, because the brittle materials are weak in tension. Okay, so here let's see the option. First is bending failure, this is shear failure, this is torsion failure, this is axial failure. So our correct option will be shear failure, because it is there is no mention of tension failure. So the correct option will be shear failure that occurs in ductile material which are weak in shear. Okay, so it takes place at 45 degree, right? It takes place at 45 degree. Moving on to our next question. The deflection at the free end of a cantilever beam of span L and is flexural rigidity EI subjected to a point load P at the free end is. So this is a standard expression of a cantilever beam acted upon by a load P at the free end. So this delta, suppose this deflection is delta, so delta is equal to PL cube upon 3EI. So we see there is no such option. There is some misprinting maybe. So here it should be the correction should be, it should be PL cube. So answer must be B after this correction. Okay, so coming on to our next question. The question says instability is a problem in. So let's see what instability is. So suppose you have a stick that's very long, and you just fix it in the ground, and just apply a axial compressive force over it. If the stick is very uh, thin, that's very slender, अगर बहुत पतला है अगर वो stick, और बहुत लंबा है, and if you apply compressive stress, then it is going to bend like this. Okay, with even if the load is well within its limit of strength, well within below its yield stress. Okay, again, even then it will bend because of instability. So let's see what's instability is. So if there is a long column and its slenderness ratio is very high, that is, slenderness ratio is effective length upon radius of gyration. Radius of gyration is suppose there is a ring. It has mass m, and there is a axis passing through its center. So the distance of this ring, that is radius at which its mass is concentrated from this axis, is about which it can rotate. This distance, this radius, is called radius of gyration. Even though the body is of some other shape, like rectangular or square or I section, these all are assumed as a ring, and this radius of gyration is found out by an expression that's taken as I by A, because moment of inertia I is equal to A into R square. Okay, where A is area of this ring or this figure, and R is radius of gyration. So moving on to our actual problem. Okay, so the long columns have very high slenderness ratio, and therefore they buckle easily. So instability is a problem in long columns. Correct answer will be option number A. Then comes our next problem. The problem says sensitivity of soil is the effect of porosity on remolding, effect of consistency on remolding, effect of seepage on remolding, effect of consolidation on strength. So let's see what's sensitivity. So by expression, if we see the formula of this sensitivity, it is defined as the ratio of unconfined compressive strength in undisturbed state to the unconfined compressive strength in remolded state. The ratio of these two is known as sensitivity. And at the molecular level, why it happens is when we remold the soil. Suppose जब भी हम सॉइल को डिस्टर्ब करते हैं, लाइक जब हम पाइल इंस्टॉल करते हैं, so there is a remolding that takes place. So it causes permanent destruction of soil solids, and reorientation of water molecules in the adsorbed layer. So because of these two, there is some strength that's lost. Okay, but after some time, some part of this lost strength is regained at the unaltered water content. So this phenomenon is called thixotropy. Okay, So sensitivity is actually the effect of remolding on consistency of clay sample at unaltered water content. So it's effect of remolding. What the option number B says is effect of consistency on remolding. So there is some mistake in this option, but we can correct it. Like it's we can understand that it means to say ऑप्शन ये कहना चाह रहा है like its effect of remolding on consistency. So we can consider this as the correct answer, although there is some mistake in it. Okay. Coming on to our next problem. As per IS 1498, silt particles are smaller than. Okay. So it says as option number A is 425 micron, 425 micron, 150 micron, 75 micron, and 4.25 micron. So we know that less than 2 micron we have clay. Okay, let's change the pen first. So less than 2 micron we have clay, then 2 microns to 75 micron. 75 micron, this is a symbol of micron, mu. So there's a silt. Okay, then 75 micron to 4.75 mm. 4.75 mm we have got sand. Okay, then 4.75 mm to 4.75 mm to 4.75 mm. Above 4.75 mm we have got gravel, then cobble, and then boulders. Okay, so let's see what's the correct option is. Okay, so the correct option is smaller than we can see smaller than 75 microns. Option is C. Okay, let's come to our next question. The question says ratio of settlement at any time to final settlement. Okay, so settlement at any time, delta small h upon delta capital H into 100. This is settlement at any time, this is final settlement. So this is a degree of consolidation. So ratio of settlement at any time. So a settlement at any time is delta H. Let us take it as delta H, and the total settlement or final settlement is delta capital H. So ratio of these two into 100 is called degree of consolidation, and its notation is percentage U. Okay, so the correct option will be degree of consolidation. So moving on to our next question. What our next question is, our next question says, in a lap joint, the bolts are in. So let us see what is a lap joint. What's a lap joint is. Okay. So suppose there are two members like this. Okay. There are two members like this, and these two members of steel are connected by a bolt. So let's see, and let's take it as bolt, and there are threads over these bolt here, and there is a nut here. Okay, so there is a nut here. So this is what is called as lap joint. Okay, lap joint. So it's asking about the number of shear planes. So see, what is a shear plane? So shear plane is where the bolt experiences the shearing action or cutting action. Suppose this joint breaks from this plane. This joint breaks from here. okay, because a bolt has been cut into two parts. Okay, so bolt cuts from this plane. So this is what is called as a shear plane. Okay, because there is a shearing action happening at this plane, or cutting action or shearing action. Okay, so in the lap joint we can see there is only one shear plane, so bolts are in single shear, and here there is moments. So there uh, if the lap joint is also an eccentric connection, so we can say there is a moment also, but we do not consider it for design. We just take, there's a shearing action, there's one shear plane to design this connection. Okay, so this is a drawback of a lap joint. Moving on to our next problem, what is a sand boiling? So it's asking about sand boiling could occur in. Okay, so let's see what's a sand boiling. So suppose there is a mass of soil, there's a chunk of soil, sample of soil, and this soil mass is acted upon by a seepage pressure in the vertically upward direction. The pressure denoted by PS. Okay, so there's a seepage pressure, and support the seepage pressure is acting upon because of the head of water. The water का head है वो है H, so वो the head is H, so the seepage pressure will be H gamma W. Okay, and because the so let's take this as submerged soil mass. Okay, so the effective weight acting will be gamma submerged into Z. So this seepage pressure will be countered by this weight of the submerged soil mass, that is gamma submerged into Z, height of the soil mass. So H gamma W is equal to gamma submerged into Z. So when these both become equal, so this is the limiting case, and if the seepage pressure increases any further, even zero point 0.1 in magnitude, then this soil will start flowing like a liquid. This soil will start flowing like a liquid. Okay, this soil will start flowing like a liquid. So this condition is known as sand boiling, or a quicksand condition, or piping. Okay, so this type of this condition, this condition takes place in just in sandy soil, because there is no cohesion in sandy soil. But in case of clay soil, there is cohesion also. So the shear strength equation of clay soil or C5 soil can be sigma C plus sigma n bar 10 phi. So there is cohesion as well. Even if this component becomes zero, okay, effective stress becomes negated, but this component is still there. So this will prevent any sand boiling or any quicksand condition. Okay, so we can see quicksand is not a type of sand, it is a flow condition. Or sand boiling is not a type of sand, it is a type of condition, flow condition, observed in cohesionless soil mass when effective stress in it is reduced to zero. Okay, effective stress is reduced to zero in upward flow condition, right? So it is found in fine sand and coarse silt, and it is not found in gravels, because gravels have high permeability, so they will easily allow flow of water through it, and they won't uh, cause any build up of seepage pressure. But in case of fine sand and coarse silt, the permeability is very less, so there will be a buildup of seepage pressure, and because of it, and there will be a sand boiling condition. And in cohesive solids like clay, shear strength is not reduced to zero, even if it is its effective stresses are reduced to zero due to inherent cohesion possessed by the particles which hold soil particles together. Okay, so as I've explained, sand boiling could occur in any type of sand, but not in gravel. Okay, then comes on our next question. In case of design of ship, it is mandatory to keep the metacenter. So let's see what metacenter is. Okay, let's see what metacenter is. So suppose we have a cylinder that's floating in water. Cylinder float कर रहा है पानी में और इसका कुछ पार्ट ऊपर है वाटर सरफेस के और कुछ पार्ट बाकी पार्ट नीचे है. So this this cylinder has some part above the water surface, that is floating in the water. So there is a center of gravity G and there is a center of buoyancy. What is center of buoyancy? Center of buoyancy होता है कि it is center of gravity of the mass of fluid that's displaced because of the floating body. Okay, so this part of the fluid mass is displaced because of this floating body. So the center of gravity of this fluid mass is known as center of buoyancy, and this center of gravity. So center of buoyancy is the point through which force of buoyancy acts. Force of buoyancy FB acts on the body, and this force of buoyancy, as per Archimedes principle, balances the weight of the body, and that's how body floats in water. Okay, otherwise it would sink in water. If the weight of the body, if weight is more than force of buoyancy, then the body would sink. And if the force of buoyancy is equal to or greater than weight, then the body will float in water. So suppose we give थोड़ा सा डिस्प्लेसमेंट देते हैं, थोड़ा सा रोटेशन देते हैं बॉडी को. सो थोड़ा सा क्लॉकवाइज अगर रोटेशन देते हैं, सो व्हाट हैपेंस इज सेंटर ऑफ ग्रेविटी तो सेम रहेगा क्योंकि बॉडी है, बॉडी का सेंटर ऑफ ग्रेविटी जहाँ से टोटल वेट एक्ट कर रहा है वो तो सेम रहेगा. बट द सेंटर ऑफ buoyancy, द डिस्प्लेस्ड मास ऑफ फ्लूइड. नाउ earlier this was displaced mass of fluid, this was the shape, and now this is the displaced mass of fluid. So you can see the mass center of gravity of the fluid mass has changed. So center of buoyancy has changed. Okay, so center of buoyancy earlier ye tha B, now this is B dash. So this is from where the force of buoyancy will act over the body. So the line of action of this force of buoyancy, cuts the vertical axis, the axis through which center of gravity passes. So the point where it cuts, this point is known as metacenter. Okay, so if the metacenter is above the center of gravity, then you can see the force of buoyancy is acting this way and the center of gravity is this. So these two are making a restoring couple that's anti-clockwise, because we had given a clockwise movement and left the body. So these two are giving a restoring couple of anti-clockwise nature. So this body will again come down, regain its original configuration. Now this is this one. Okay, so it will again regain its original configuration. So for stability of the floating body, the metacenter must be above the center of gravity. So design of ship की बात हो रही है, so ship obviously stable होना चाहिए. So we have to keep the metacenter above the center of gravity. So इसके लिए डिज़ाइन करते हैं, इसके लिए इंश्योर करते हैं कि सेंटर ऑफ ग्रेविटी नीचे रहे और ताकि मेटासेंटर ऊपर रहे हमेशा. Okay, so this was your 38th question. There is some the pages are displaced. So the earlier questions which we have skipped will come later on. Okay, moving on to our next